All right, so maybe I think we can just start at the top, okay? All right, so let's start the first talk, okay, for today. So, by the way, there's a change of the schedule. Lai Wang Jing flight was delayed, so he cannot give the first talk. So the first talk, the 11:20 talk will be given by Harada, okay, and Lai Wang Jing's talk will be switched to Wednesday evening, okay. All right, anyway, so the first talk will be given by Professor Stephen Smith. Okay, he will talk about Bob's work on simple group and their classification. So let's talk.
It's a very great pleasure to be here in Taiwan, especially Dr. Bob Griess, valued colleague and friend for 43 years and counting. Anyway, Bob's been on a record, I think it's been about Yeah, ever since I was a student and started coming to these conferences, I saw that there's a danger always of the old timers getting up and reminiscing about the good old days. Of course, now I am an old timer, so it must be time to start reminiscing. Okay. Well, I think. Not yet. Oh, yes. Oh, just wait.
Oh.
Okay, it was back in the spring of 1973 when I met Bob. We're not sure of the exact date, but in going through the archive, I came up with this historical document. It is lecture notes that I took on a talk by Griess on extensions of groups, and the date is 31 May 1973. So, probably before then.
I think that was not so.
Okay. The story is, of course, I was a finishing graduate student in Oxford in spring of 1973. And at Warwick University, 40 miles away, there was a special year in group theory. So it was a huge honor for me to have them come to Oxford, and I would go to Warwick theory talks. I got to meet all of the senior people in the field pretty much. Of course, Bob was only 2 years past his degree, but he was already pretty senior. His work was extremely well known. So we'll get back to that in a minute. I don't want to actually get on the work now. There are some things I found in the archives. I guess after Oxford, I went to Caltech for 2 years, and then in '75, I came to Chicago, to UIC, or UICC as it then was. And of course, Bob was already at Michigan, so this was extremely convenient because it was easy to go to Ann Arbor, visit Bob, and came to Chicago a lot. So over the years, we've seen a lot of each other. And of course, that means there are these old photographs. You can perhaps see them a little bit here, but let me enlarge one. Okay, some of you remember Pat McBride, and his wife Malin, and Bob, and a young lady I had met comparatively recently. This is from the same 1977 time. Okay, so how about a little later when Bob was entering into a new role? Some of you know Peter. Okay. He probably looks a little different now. I'm not sure why. Okay, and let's see, let's move forward to 1990. Okay, Peter's a little older now. We'll get back to that. So here's a picture of Bob that I particularly like. Again from 1990. Finally, let's move to 1993. Okay. It's at this point, before the talk actually starts, that we have a little quiz. How many people, hands up, think that Bob looks different now? How many people think that's exactly the same? Okay. The timeless, ageless Bob Griess. Okay, so there actually will be a talk eventually. That's it. All right. here is what I plan to try and do. Do a little introduction here so that I can say a little bit about Bob's earlier work on Schur multipliers. Then some things on standard form problems. Then a bit, of course, on Monster. I'm not going to try and do the Vertex algebra stuff because almost everyone else in the room is way better equipped than me to talk about that. But I'll mention it briefly. Also, I'd like to at least mention by the end for different kinds of sporadic situations that Bob's been interested in. And a little bit about the work on embedding simple groups, particularly in real or complex Lie groups. Alex Rigo, of course, is the collaborator on that, so he'll be the main talk on that area. Okay, and I guess I'm saying here, don't take notes. These stuff is all on the web. Okay, my comment about historical artifact number 1 here was, in those days we did take notes by hand. And I've often wondered, was I ever going to use these things again? Well, the answer seems to be, when you retire and you go to conferences for journal, then you'll be able to hold them up. So that may be one reason to do it. Okay. All right, so just as background here, it's sort of convenient for things I want to mention about classification to refer to the outline book that Ashcraft Ryan's Solomon and Smith-1. Okay, and the choice of this topic, well, if anybody can now go to Math Synapse and look up all of Bob's 85 papers, over half of these are about simple groups one way or the other, and even the Vertex algebra stuff is largely motivated by simple groups. But of course, with that many papers, 40 plus, I'm not going to say a whole lot about each one. So it's okay, I'm going to skimp on the details. Okay, so we want to talk for a second about quasi-simple groups. And this may be really boring for everybody, but if you're going to study simple groups, quasi-simple groups come up pretty quickly, for example, among subgroups. So quasi-simple group is just a group whose quotient one center is simple, not really simple, and is perfect. Okay, and they do come up, even if you're looking at simple groups. Particularly the most famous that I'll talk about today is a quasi-simple group which is subnormal in X. That's called a component of X. And components often arise inside centralizers like involutions or elements. A log order, that's one reason they're important. So even though we're studying simple groups, quasi-simple groups are there. Okay. Well, the components in a group commute with each other, and they're the factors of E of X. And that's part of the generalized fitting subgroup, E of X times F of X, where F of X is the classical fitting subgroup, namely the maximal nilpotent subgroup. And the importance of this is the generalization of fittings done to general groups, that the generalized fitting subgroup is self-centralizing. So what does that mean in practice? Well, the generalized fitting subgroup kind of has to be there. Suppose F star of X was trivial, then its centralizer would be the whole group. Okay, and if it was trivial, the whole group would be trivial. So it's there. If the group is non-trivial, the generalized fitting subgroup is non-trivial. But also because it's self-centralizing, think about it for a second, X can't just ignore F star of X. It can't sort of put it off to the side. X modulo the center embeds faithfully in automorphisms of F star of X. So again, probably everybody knows this stuff, but it's actually important in several ways in the background talk today. So F star of X is some important part of the group. Okay, when X is a B over subgroup, one condition we'll see is when F star of X is just a B group. That's, so it doesn't have any quasi-simple parts, it doesn't have any nilpotent parts, co-prime. Okay, well that's just a little bit of background to set up the first part here. With regard to classification in general, it's perhaps kind of obvious that what you have to do is start with the answer. So skip forward to what the list is, and then show that that list has to be complete. So what is the final list? Well, again, probably everybody knows this, but we'll say it. They're the alternating groups, and at least 5, they are simple. They're the Lie-type groups, sort of classical things like orthogonal and linear and symplectic groups, and also exceptional and twisted types. They're all matrix groups over finite. And finally, there are the 26 sporadic groups, which we'll later. vernacular world today. They don't fit into any of the families. Anyway, I'm going to use the letters ALS to sort of talk about the three cases as we proceed. So the classification problem is, if you believe the list is complete, you have to prove it. And you can do that by induction. Now, historically, the relevance of this is, Bob was finishing up, I think, in 1971. And at that time, this list, although it's sporadic form, it was not known to be complete. Or it wasn't complete because the monster, I think, nobody had any early before about 1973. Okay, so that was an obstacle to classification. But during the 70s, people got pretty sure that the list was complete. Okay, so I'll talk now about Bob's famous early work, sure multipliers. So if S is a simple group, and L mod center is the S, how big can L be? How much larger than a simple quasi-simple term would be? The answer here is classical. Really, a way of phrasing it is how big can the center be in such a quasi-simple group covering the simple group? Yes. And it's the Schur multiplier. Schur probably, what, like 20 or so generated the theory. And what's the final answer for the non-simple groups, the simple groups? Well, again, you can look in the, I think this is the third volume of Bornstein, Lyons, Solomon. So the answers are there. But as I say, in 1970, when Bob was doing his work, couldn't be complete because we didn't even know all the simple groups yet. So what happened, and I'll expand slightly on this in a moment, there were various authors treated various cases. But really it was Bob that kind of finished it off and became the standard reference. So that's the theme of the first part of the talk here. I won't be able to go into detail, but maybe a little bit. Okay, so the alternating groups, I guess, was a big motivation for sure doing this work, to say what can be a larger cover of an alternating group. And usually it's just a double cover. But in the case of 6 and 7, you can actually do 6-fold cover. So that's classical, I guess. 1911 already. Sporadics. Now, how are they done? Well, usually when someone discovers a sporadic group, that person or persons would find the multipliers. But Bob did some work on various sporadic groups. There's a bibliography at the end of this talk, so you can look up the papers there. Or go to Math.net. Math.net, anybody can write this talk, so you want to write a program to write this talk. I haven't done by the end. Oh, the lead time. Okay, well, Steinberg did a lot of this. Mostly the part that can be done straightforwardly by lead theory, but there's more that has to be done. And Bob's thesis was basically in that area. And continued in later papers. And these three papers are, I guess, what a lot of people use as the standard reference. Okay, I looked in the outline book on the classification, about 2 dozen references there to I did some of my own papers, quite a lot of them did that, so that is a sort of quick overview of, I think, the work for which Bob first became famous. What can I say about it? Well, it's kind of, you did these one at a time. It's probably too technical to go into. You can look in GLS to read a bit more. Okay, and I would like to touch on get back to the multiplier of S as a topological description. Okay, homology of a simple group in the integers, or the cohomology, second cohomology, and the complex number. So a lot of standard finite group theorists, like me especially, who are pretty ignorant of topology. But Bob actually was an expert early on. And there are other kinds of non-split extensions, particularly group extensions over national modules, or various kinds of modules. And non-split is the extension will correspond to non-zero cohomology groups there also. Yeah, you can search this. Basic expository groups is probably not. Well, Bob did become one of the big experts. Okay, and in particular, strange things that happen in cohomology tended to correspond to strange configurations that came up in strange sporadic groups. So I was going to, I think, show you a another historical artifact. This seems to be a note from a Northwestern talk about June 2nd, 1976. Survey of recent results on HM, GM, group in module M, n equals 1 and 2. So this is a big dog-eared, old-fashioned Xerox copy that I kind of used as a basic reference for years and years and years and years. There were other references, and I should mention them. Okay, especially in the type case, finding partial slot and joint partial got mentioned a lot. This makes it convenient for me to go with what before Scott's talk later on in the conference. Okay, and I'll try to get back to a little bit of this later in the talk. Depends on how the time is. I'm doing okay at the moment. Okay, what about standard form and standard type? Well, here I want to give some background also. Again, possibly it's familiar to everybody, maybe not. But I think in colloquial level I should say, what is domain case division in the classification of simple groups? It divides up into sort of odd and even branches. What does that mean? Well, again, a better place to study this in detail would be chapter 0 of the outline book, where we got to go through the arguments, which are not terribly difficult. Can't do it in an hour, but yeah, look at it. It's done in comparatively few pages. Okay, anyway, where would we start with a simple group? Well, it has to have even order because we have to fight Thompson theorem. So there has to be an element order 2, or an involution. Okay, the centralized involution is not simple, it has to be a proper subgroup. And by induction, if you're trying to prove what simple groups are, you know what the simple sections of the centralized are. So that suggests an approach. Well, first of all, describe all possible groups inductively H with an involution X in the center that could be a centralizer, and then for each such H which could be a centralizer, find out the groups G in which it is a centralizer. Okay, so at some very far removed, this is the way the classification is. Well, if you take a normal series, each quotient is a section, so simple composition factors, if you like. Do stop me if I'm not trying to throw out undefined terminology. Make sure I'm honest. Okay, so if we look back at the case list ALS, most of the groups by any reasonable measure are latent. So matrix groups are kind of the target model case. Okay, so what I wanted to do was take an example to try to show what the case division looks like in practice, in examples, and then try to extract from that. Okay, so look at just the linear group. I appreciate the linear group is not going to be simple. You have to go to the determinant 1 part and then move on center, but it's close enough for expository purposes. And let's look at the odd case. Take a diagonal matrix with k minus 1s and n minus k 1s. Actually, from an old talk, I should have a slide of this. Oh, sorry, let's go back one page here. Not where I want to be. Let's do this. No, that's what I wanted down. There we go. This is exactly what I said. So here's the involution T I was talking about. K minus 1s. Of course, squares to the identity, so it's an involution. What does a centralizer look like? Well, it's easy linear algebra. Anything that commutes with that has to preserve its eigenspaces. So that basically means you get zeros in the off-diagonal box. Until you get a copy of GLK and a copy of GL and minus K. And this sort of brings up the what happens in the odd case. If you look at an involution centralizer, you expect these SLNs. We'll go back to the main talk here. Those SLNs are quasi-simple. And they are normal. They agree with each other in this case. Those block matrices that are here and there. So basically, what I'm saying is here the SL is a component. It's quasi-simple, and it's even normal in this case, but it's in particular subnormal. Okay, so how would we extract this to something we might be able to work with in a proof? Well, we say a group is a component type if there's some involution and the centralizer of that involution modulo O2 prime, that's just the largest normal subgroup of order prime 2, that has a component. Why modulo O2 prime rather than the center? Well, that's a technical thing that comes up in the argument. I don't have time to review today, but it's pretty easy if you go to the outline book, for example, chapter 0. That's a simple argument. It goes through that. Okay, so the notion of component type does get most of the beyond part of the weak type groups. It's a matrix group over a field, a lot order should be there. But if you think about it for a second, it's also true of the alternating groups. You take sort of 1, 2, 3, 4 as your involution, and that's centralized by an alternating group on n minus 4 letters. And at least 9, that's going to be okay, and some sporadics have components as well. So it's not a perfect correspondence with the odd matrix groups, but abstractly, it's close enough for our purposes. What about the even case? So if you look at that example of the diagonal matrix, in characteristic 2, minus 1 is the same as 1, so that's not order 2 anymore, it's just the identity, minus 1. Okay, so what would we use for an involution there? Well, if you should take a minimal short block of order 2, just sort of 1, 1, and a 1 below the diagonal, and the identity everywhere else. Actually, that's a conjugate to a more convenient version. You move the sort of minus 1 just below the diagonal all the way to the bottom. And again, I should have a picture for that one in the old block. Let me bring that guy back up. Oops. This one. There we go. Okay, so now for the even case. All right. So if we put the 1 down to the bottom, we've got the identity in the sort of middle block. What centralizes that? Well, it's not maybe obvious to the naked eye, but if you work it out, what happens is you get things that are non-zero possibly here and there. This might look superficially like the other case, in that there's now a GLM minus 2 there. But that GLM minus 2 is not normal. For those of you that know the Lie theory, this is actually a parabolic subgroup. The normal 2 subgroup, U, and the complement there, which has the zeros in the off-diagonal blocks. And if you take one of these guys and conjugate it by one of these, you'll start to fill in non-zero stuff. So it's not in the group, it's not normal. So even though there's a big quasi-simple subgroup in there, it's not normal anymore, and that begins to express the difference between the even and the odd case. Okay, what actually happens, and now I think we can go back to the top itself, where we were. Okay, so central is a product of a 2 group, and use this sort of quasi-extra special notation. You don't need to know what that is, but recognize it. With a subgroup which is not subnormal. So what's actually happening, it's a group of characteristic 2 type, because if you look at any involution, basically a similar thing happens. The F star subgroup in the abstract product of the E and the X is just a 2 group. So the E part is trivial, there are no quasi-simple normal, quasi-subnormal subgroups, and there are no normal subgroups to be a fitting part. And it turns out this condition on the involutions is the same as having it for all 2 levels. That is, all normalizers of non-identity 2 subgroups. So this is an abstraction of what we saw in the example. And characteristic 2 type, in fact, does get pretty much all of the P equals 2, that is, V-type groups defined over finite field of characteristic 2. Okay, and they're very sporadic as well. So if you're looking to divide the simple groups into 2 cases, these abstract definitions of component type, characteristic 2 type, do a pretty good job. Okay, so the question becomes, if it works for the examples, how do you make it work by proving that everything is there? And this is a dichotomy theorem. Again, you can see a more detailed derivation of this in the outline book. What it basically says that if you have a simple group and the 2 rank is at least 3, so here the idea is we want to avoid small cases. 2 rank 2 means what? It means you can have a 2 group with Rank 1 would be cyclic or Quaternion, or rank 2 could have Z2 plus Z2. Okay. And groups like that were handled sort of early on in the classification. I guess various people should be mentioned, Bernstein, Lance is in there. So that was done. So once you go beyond that, then it's possible to prove that group G is either of component type or characteristic 2 type. So the abstract definitions do divide into two cases. Component type is basically the odd case, characteristic 2 type is the even case. And that's really the two halves of the classification, which is jumping off point for part 2 of this lecture. Okay?
Why is the how do you prove the dichotomy theorem?
Say again?
How do you prove the dichotomy theorem?
Well, that's in chapter 0. I can give you a very quick thumbnail sketch, but the idea is if you deny everything to deny one, if you want to deny component type, so there are no components, so that means in an involution, if you look modulo, so there's no E part, so you have only an F part. So if the F part has no odd part, it's only a 2 group. So that's what you want to prove. So you have possibly a simple group acting non-trivially, non-centrally on an odd group. So you want to show that those odd things are all trivial. When you define a graph and use the rank 3 this way, with the centralizer is something of rank 3, you see what the odd part is. If you define a graph by rank 3 groups intersecting in rank 2 groups, and you sort of put the transitivity on that graph, this is an idea basically signalizes numbers going back to Thomson. So if the graph is disconnected, you get characteristic 2 type because it's a strongly embedded subgroup. If the signalizer functor is non-trivial, basically an early theorem, signalizer functor theorem, said that that thing has to be determined sort of uniquely, and it's sort of determined by this connectivity over the whole component. Okay, and that would make it a normal subgroup of odd order of the group, but you're in a simple group, so that can't happen. So it's sort of a connectivity argument, which I haven't been fair to Hunter.
So this was a real theorem around what, around 1971, and you didn't have to quote an induction, or you didn't have to quote any later.
Correct. Yeah. So the ideas go back to Thomson. Bernstein, Walter developed them, I think, in the GLS books. This kind of argument leads to what's called the Bernstein-Walter alternative, and basically in this case, these are two alternatives. One is if you deny the component type, then you come up with a characteristic type. So, I think we're doing okay with that. So I apologize for the cavalier nature of that. So now we'll return to the procedure that was in progress. We have two halves of the classification left after the small cases are done. What about the odd half? Well, there are complications there, which again I'm going to really wave my hands at. But in effect, the component type case was reduced to what Ashcraft called a standard component. I'm waving my hands at things like the Amdahl's groups and the unique conjecture, sort of considered standard. Two components, but standard form for Ashcraft was roughly this. I'm reading Harris, but some involution centralized as a component, which whenever you have two conjugates of it, they don't work, and the centralizer of the pair of them has odd order. So you can kind of see that from the diagonal matrix stuff that I did before. If you sort of put your two minus ones up in the corner, you get a big GLN minus 2 here. If you put a different 2 down in the bottom corner, you get a big GLN minus 2 in the upper block, and they intersect, so they're not going to compete with each other. Okay, and whether they centralize in general in that case, no. But I mean, this is the spirit of it. So what it does mean is that if you take such a maximal thing, you get this standard form, these extra conditions for a suitable maximal component. So the idea then is, if you know you get a standard component, you can take each simple group and say, well, what group can this be a standard or some actual cover of it?